Hi everyone, welcome to this talk. Our goal today is to build a model to understand the evolution of a population. According to Darwin, two strengths play a crucial role in evolution. It's mutation and selection. Mutations are here to constantly discover new behaviors, and selection is here to sort the good ones from the bad ones. To evolve, there must be a balance between these two forces. If mutations are too strong, the good individuals, the ones that take advantage of their environment, will not have time to thrive in the population because when they reproduce, they mutate. If selection is too strong, a change in the environment and the population will not have enough time to adapt. What we're going to see is a probabilistic model where this balance translates into a phase transition. The works here are based on the one of Manfred Eigen in the 70s. He's the one who introduced the term quasispecies and the specific conditions that we're going to study here. So what we need is a population made up of individuals. We'll consider here only genotypic model, which means that the behavior of an individual will entirely be determined by its DNA, which is a finite sequence of zeros and ones. What we need is mutations. We say that when an individual must undergo mutation, all the bits of its genome will be randomly changed with small probability q, independently of others. I think that the genome will be a big chain, the length will go to infinity, and the probability of mutation will go to 0. Now that we have mutation, we need selection. We'll consider here only what we call as the sharp peak landscape. It means that only one sequence, say the one with only zeros, that we call the master sequence, has a genetic advantage. It's coded by a parameter sigma. This parameter will represent selection. So Manfred Eigen implemented this principle in differential equations, working with proportion of individuals. And by changing the asymptotic regimes per parameter, he observed a critical change in the asymptotic behavior of the population. More precisely, there exists a critical parameter, Q star, which is log of sigma divided by L. If Q is the parameter for mutation. If Q is greater than Q star, then the population is completely random at equilibrium and no master sequences are present. If Q is smaller than Q star, master sequences occupy a positive proportion of the population along with a cloud of mutants that are genetically close to the master sequence. It's what Eigen called the quasi-species. This graph represents the average number of each Hamming class. So we say that Hamming class K gathers all individuals with K1s in their genomes. And the horizontal axis is the limit of the product L times Q. So it's the average number of mutation of change in the genome when there's a mutation event. And look at the graph and we see that when Q is very small, then master sequence occupy nearly all the population. And when you increase Q, you see the cloud of mutants here. So the green curve is all the individuals with one in their genome. And you see here the critical point, log of 5 is approximately 1.6. And past this point, there are no master sequences in the population, no class 1 or 2. All individuals are in class L divided by 2, so they are completely random. So this phase transition is a first order approximation. Q star is defined by, before Q star there are master sequences and after there are no master sequences. What we try to do is try to compute the critical exponents of the model. How, when the parameters go to their limits, the critical points go to its limit. So what we're going to do is implement the principles that we just saw in discrete models. We could do this in different discrete models such as the Wright-Fisher model or Galton-Woodson trees, but we'll focus on the Moron model. The Moron model is a discrete model. At each generation, the population follows 3 steps, which are repeated infinitely. First step, a parent has chosen the population. It's here that selection enters the game because master sequences are chosen preferentially with parameter sigma. Then the chosen individual gives birth to a child which undergoes mutation. So each bit of its genome is changed independently with probability q. And last step, the offspring replaces an individual chosen uniformly in the population. This keeps the population size constant over time. So the funny thing is that in a proper asymptotic regime for parameters, these 3 simple steps are sufficient to observe the same phenomenon of phase transition as eigenquasispecies and with the same parameter q star, log sigma divided by L. But the model allows more because we have the size of the population now that is finite. So it would allow us to give the correction term of the error threshold due to the finite size of the population. Actually, several definitions of error thresholds are possible and they would lead to different correction terms, but let's see one. Let's follow a population over time. 2 phases alternate. When there are no master sequences in the population, then all chains play the same role. It's the neutral phase and lasts until master sequences are discovered with mutation. It takes approximately 2 to the power L generations, which is the number of all possible chains. So no selection in this phase. And then you have the quasi-species phase, where master sequences invade the population along with a cloud of mutants. And it lasts until every master sequence is replaced. So we like to think of these 2 phases as the balance between mutation and selection. You see that the quasi-species phase is the place selection is in the model and the neutral phase is only mutation. So actually we like to think the phase transition as the point where these 2 phases are equally stable. We could measure the stability of these 2 phases by their duration in the how many generations it needs to go from one phase to the other. And actually, it works because if the parameter for mutation is very small, then the quasi-species phase will last very long because the offspring of master sequences will often be master sequences. If you increase the parameter for mutation, then this time decreases. And when it reaches 2 to the power L, it means that the 2 phases are equally stable. And that's our definition for the critical point. So the difficulty here is to compute the survival time to 0. With Hamming classes, we have reduced the huge state space our population evolves in. It's legit to work with Hamming classes because transition probabilities depend only on the Hamming class of an individual. How many ones do you need to change in zeros? It's not where the ones are located in the genome. But we are interested only in the number of master sequences in the population. And sadly, the number of master sequences is not a Markov chain because in order to understand the evolution of this number, you need to know the complete representation of the population. So what we do is we're gonna build 2 Markov processes that will bound from below and above the real number of master sequences. So let's first focus on the lower band. In the lower band, we say that, okay, master sequences can reproduce and mutate, but non-master sequences will never give birth to master sequences. Of course, when you do this, you have less master sequences in your population. And for the upper bound, you do the contrary. You do that. Every non-master sequences can give birth to a master sequence as if it had only one in their genome. Only one to change. In real life, the cloud of mutants, as you saw on the graph, is occupy a positive proportion of the population, so mutant could recreate master sequence. But these two bounds, the common terms of these two bounds will not see this phenomenon, and actually it will be enough to have the first term of the development of the error threshold. So these two bounds are great because they are birth and death chains, and there exists explicit formulas to compute the average time needed to reach any point. So with this explicit formula, we managed to have an estimation of the time to 0. That's roughly this. And remember that the time of the neutral phase was 2 to the power L. So by comparing them, we have an asymptotic development for the critical parameter Q star. So we have a correction term in 1 over square root of Lm, where L was the length of the genome and M was the size of the population. So you notice that if M is infinite, you just find the log sigma divided by L back. There exist other possible definitions for critical parameters. For example, if you increase the parameter for mutation again, then the time tau 0 needed to see all master sequences disappear will decrease again, and you could look for the parameter needed to get this time bounded by a constant. And actually, this is the parameter that counts in real population, because as soon as you lose the master sequence, well, you probably extinct as a species, because other population then take better advantage of their environment than you. So, however, yeah, the two bounds are, we need smarter bounds actually to compute this point, because of course we need a much better estimation of the time to 0, and I hope that I will be able to show you this soon. Thank you for attention. I hope to see you soon.